In this video lecture, we'll be discussing a paper published in EJOR, and the title of the paper is Deep Reinforcement Learning for Inventory Control, a Roadmap. So I'll start with what reinforcement learning is. So RL is an area of machine learning that focuses on sequential decision making. So how that occurs is we have an environment, an agent, a reward, a state, and an action. These are the four parameters. So for example, an environment reveals a state S. Observing that state, the agent takes an action A, and on taking that action receives a reward R, and the state of the environment then changes to S dash. So on and so forth. This continues, and the aim of RL algorithms is to maximize this cumulative reward. So RL algorithms prescribe what to do, like what actions to take from the action set that maximize this cumulative reward. So next we come to deep neural networks. So deep neural networks are a supervised machine learning technique. So they have an input layer, one or more hidden layers, and an output layer, as you can see in the diagram. So each node in a layer connects to each node in the subsequent layer, and there is some weight associated with it. So due to these connections, each node in the subsequent layer gets activated by some magnitude. So for example, by the activation level of nodes in the input layer, some combination of nodes will be activated highly in the hidden layer 1, and because of that combination, some different combination will be activated with different magnitudes in hidden layer 2, and finally we'll get an output. So this goes on, and we see different activation levels in the final layer and so on, and we see a different output. For example, you can see this example. So input, we have some matrix of pixels, and each pixel is activated differently by what is written by, you can say, it is easy for us to see that the number written on the pixels is 2, in the image is 2, but how will the computer be able to identify it? So the input layer is different activation levels of each of the blocks of that image, and due to this different activation level, you can see x3 and x4 are highly activated nodes, and due to this combination there is some different activation level achieved in hidden layer h1, and then different activation level achieved in h2, and finally we get an output layer. So in the output, you can we have 10 numbers from 0 to 9. So our algorithm is predicting what is the probability of achieving different outputs. So we see that the probability that the number is 2 is the highest, so it predicts the number 2 to be the answer for this. So in this way, this is the way how deep neural networks work. So the paper focuses on something called as deep reinforcement learning. So it is basically solving the reinforcement learning problems using deep neural networks. So how is it relevant for us? So this technique can be used in operations management. So the core idea of OM is to match the supply and demand, and that is done by inventory control. So as I talked earlier, the action that the agent takes is inventory replenishment decisions, and the reward that he achieves are the savings on inventory costs. So the aim of this paper is to discuss how deep reinforcement learning can help in inventory control. There are two main constituents of deep reinforcement learning, and these are Markov decision processes and neural networks. So MDPs are the model or language in which the problems solved with DRL must be expressed, and neural networks are used both to express and to find approximate solutions for these problems. So in Markov decision processes, we have a state S, a small s, that belongs to a set of states, and an action A that again belongs to a set of actions. And there are two types of policies. So a policy can be deterministic or stochastic. So what policy tells us is, for a given state, so if the policy is deterministic, if we are in a given state, what action to take. But if the policy is stochastic, so if we are in a given state, what is the probability of each action that should be taken in that state. So MDPs, they define some certain functions. So first is the state value function. So again, so value of a state under policy pi. So it means that for a given state, what is the probability set of actions. So for example, I'll start with two states, S0 and S1. So S0 is at time t equal to 0, and you can assume that inventory is I0, and there are different actions available for the agent, Q1, Q2 and up to Qn. So policy pi tells us that what is the probability of choosing each action in that particular S0 state. So I'll order Q1 with probability of P1, Q2 with probability of P2 and so on. So that is my policy. And based on that, I'll get some rewards, and that will be the value of the state S0. After taking these actions, I'll go to the next state S1, that will be at t equal to 1. I'll have inventory I1, and there will be again some actions available to me that will be different order quantities, Q1, Q2 up to so on. Again, for the policy, I'll have different probability associated with each decision, and I get the value of state S1. So I'll go to the paper now. So you can see in the red bracket, so how we are defining the value of a state. So so the first term, first we have to see that value of a state is the summation of all the actions, value of all the actions in a given state. So if there are a capital set A of actions, so for taking a small action A for a given state, we have some probability. So that will be this probability, and we have some cost associated with it. And what is the you can say the reward of the subsequent states. So that will give me the value of each state, V of pi. And this is solved using the Bell-Mel optimality equation. So V star of S. So we find the set of we find the actions that so in this case we are minimizing the cost. We find the set of actions that minimizes this cost. So the next thing we come to are value action functions, action value functions. So it simply means, so if we are following a policy pi, so what is the value associated with each action. So you can see this in the green bracket. So if I'm following a policy pi, if I'm following a policy pi and I'm in a state S and I take an action A, what will be the value of that action? So there will be some cost associated with it, and then there will be some future probability of going to state S dash and summation of all that, and all the, you can say, the values of actions associated with the future states. So this is the way we define the action value function. At the end of the day, what we want to achieve is the optimal policy pi star. So if I am a given state, what should be the probability of each action that should be taken that will minimize my total cost. So that is represented in this equation. And for solving this equation, we have different methods, so it depends upon the complexity of the situation, of the problem. We have four partially overlapping approaches. So the first is analytical and exact, second analytical and approximate, numerical and exact, and the final is numerical and approximate. So the deep reinforcement learning belongs to the class of approximate numerical methods. Now we come to the use of neural networks. So as discussed, there will be an input layer and an output layer, and in between there will be multiple hidden layers. So I've taken here two input nodes and two nodes in H1, two nodes in H2, and two nodes in output. So each node of the input layer will be connected to each node of the H1 layer with some associated weights. So W11, W12, W21 and W22, and there will be a bias associated with it. And so this psi naught will be the value of or the, you can say, the activation level of state 0, and psi 1 will be the activation level of state 1, and so on. So we are left with these parameters, and so this is the parameter matrix or parameter tuple. So I'll go to the paper now. So output of each layer L depends on the activation function f, and it is a combination of the weights, the output of the previous layer, and the bias. So in this way we keep on getting the values of or the output of each subsequent layer, and finally we get the final output. So DRL can be used for solving different aims. So for example, the first aim can be in value-based methods. We see that we can use neural networks to represent the action values, and we search for the approximation of optimal value functions and not the optimal policy. So conversely, in policy-based methods, we represent a policy pi theta, and we try to approximate the optimal inventory policy. So we can see this in the diagram. So for example, so this is the action value. So we have some initial states, so there will be some bias associated and some weights for each of the edges, and as an output we have different action values. I have different values for each action, and here we can like sort of identify what will be the optimal action for a given state. So conversely we have something called as conversely we have this we have the stochastic policy pi theta if we want to identify what should be the value of pi theta, and we have again some initial states, some weights associated, some bias, and some hidden layers, and we finally get the probability distribution of different policies. So for example, if we have these states, and if you minimize the total cost, so this policy should be followed, but we can see that this policy also not far away from achieving the optimal costs. There are different types of DRL algorithms DRL algorithms, and they have different design specifications. So for example, one specification is the algorithm offline learning or online learning. So in offline learning, the algorithm trains on previously collected data, but if the training can be done on additional data that is collected during learning, the algorithm is also online learning. The second specification is the algorithm model based or model free. So in model based, an agent can predict what will be the outcome of each action before actually performing the action. So in model free, the agent needs to carry out an action to see what happens and then learn from it. And one final design specification is the algorithm off policy or on policy. So in on policy, the recommendations of only the current neural network are used, while in off policy, experiences generated using different policies can also be used. So based on these specifications and the requirement of the modeler, different algorithms, the algorithm that best fits the need can be decided. Now we come to the section of avenues for future research. So deep reinforcement learning can be used for data-driven inventory control. So traditionally, inventory control models, they assume a distribution of uncertainty. That is, so either the demand or lead time is to be known and a pre-processing step is required. But using DRL, both steps are no longer made sequentially, but they are integrated. So one possible use is leveraging big data to enrich the state space. So for instance, using DRL, we may add historical demands or lead times and exogenous data such as weather, news events, competitor activity, and so on in this state space. So that may give better results. Additionally, the aim can be modified to develop more robust policies. So in robust policies, we consider the worst case cost. We minimize that instead of minimizing the total expected costs. And DRL can be used to develop policies for dynamic environments. So we see that demand distributions evolve over time, and future research may focus on developing the DRL algorithms that can cope up with non-stationary environments. So second major future avenue of research is blending the numerical and analytical approaches that optimize inventory policies. So we can use the analytical results to improve the DRL performance, and integration of these results in algorithmic design can steer the DRL algorithm into the right direction. So for example, we may inject the analytical properties into DRL algorithms by shaping the value function through smart elimination of suboptimal actions or states, by penalizing the loss function when its shape does not resemble the desired structure. Additionally, we can use DRL algorithm. We can extract simple heuristic policies from DRL algorithms. So the numerical policies developed by DRL may be used for this, and these heuristics which we obtain are easier to implement. And we can reverse the trend of benchmarking these new approaches against existing policies, and we can use DRL to benchmark the performance of existing heuristic policies and understand why or when these heuristics perform better or worse. And DRL can also be used to the DRL policies that we obtain are notoriously difficult to interpret. So research is required that explains these DRL policies. So models and that explain why some action is proposed can be very helpful, and these will provide managers with the intuition. If they have the intuition behind the action, then adoption of DRL will improve. So the final research avenue is the scalability of these algorithms. So the different training algorithms that we discussed, so they have not been studied that well. So for example, PPO requires less tuning compared to A3C. So but the research in this area is still very preliminary, and there is a requirement for improving the training performance, and structural knowledge of the heuristics. We may use the structural knowledge of the heuristics that are known to perform well for this task, and additional research is required if we want to extend to large action spaces. So these action spaces arise when there is no upper bound on the proven no upper bound can be proven on the size of the orders, or when this upper bound is very large, or if we have a continuous interval. So discretizing the set of potential orders may lead to theoretical performance loss. So, and additionally, if there are multiple actions to be taken, for example, multiple SKUs, or when inventory at a location must be allocated for shipment to multiple downstreams. So in these cases, the action space is quite large, and research is required to develop algorithms that provide solution for these large action spaces. So now we come to the conclusion section. So in this paper we saw that the applications of DRL algorithms in inventory control is quite scarce, and we saw how neural networks can be effectively employed as an approximate numerical approach to optimize inventory problems that are modeled as Markov decision processes. And we also discussed the essential design choices of the DRL algorithms, and additionally we saw what areas or what avenues are research is required and that has not been explored to date. Thank you.